What if the mysterious object racing through our solar system isn't what it appears to be? Fresh observations of 3I/Atlas are revealing characteristics so unusual that some scientists are questioning whether we're dealing with a natural comet at all. This interstellar visitor's trajectory, timing, and behavior patterns are defying conventional explanations, leading to heated debates in the scientific community. Today, we'll examine the mounting evidence that suggests this cosmic wanderer might be far more extraordinary than anyone initially imagined, and explore the controversial possibility that we could be witnessing something truly unprecedented. Discovery and initial detection. The story of 3I/Atlas begins with a routine sky survey that would soon turn extraordinary. On July 1, 2025, the Atlas telescope system at Rio Hurtado Observatory in Chile captured images of an unusual fast-moving object designated A11PL3Z. Larry Deneau from the University of Hawaii's Institute for Astronomy immediately recognized that this wasn't an ordinary solar system object. Within days, follow-up observations confirmed what astronomers had suspected. This was the third confirmed interstellar visitor in human history, joining the ranks of 1I Oumuamua discovered in 2017 and 2I Borisov found in 2019. The object received multiple designations, 3I Atlas for its interstellar status, and C2025N1 for its cometary characteristics. What made this discovery particularly intriguing was that despite entering our solar system weeks earlier, 3I Atlas had remained undetected due to its challenging viewing angle against the dense star fields near Sagittarius. John Tonry, principal investigator of the Atlas project, noted that pre-discovery images dating back to June 14, 2025 revealed the object had been silently approaching our solar system for an extended period. This late detection would prove to be just the first of many unusual characteristics that would set 3I Atlas apart from any cosmic visitor we'd ever encountered. Extraordinary orbital characteristics. Prepare to have your mind blown by the absolutely extraordinary orbital mechanics of this interstellar wanderer. Davide Farnocchia from NASA's Jet Propulsion Laboratory has calculated that 3I Atlas follows a hyperbolic orbit with an extreme eccentricity of 6.14, the highest value ever recorded for any known interstellar object. This mathematical measurement indicates just how dramatically different this visitor's path is from anything bound to our solar system. Even more remarkable is its incoming velocity of 58 kilometers per second, making it the fastest interstellar visitor ever recorded approaching our cosmic neighborhood. But here's where things get truly suspicious. The trajectory lies almost perfectly within the ecliptic plane, the flat disk where most planets orbit the Sun. Marco Micheli from the European Space Agency has calculated that the probability of this alignment occurring by random chance is merely 0.2%. This isn't just unusual, it's astronomically improbable. Most objects from interstellar space would approach from random angles, yet 3I Atlas chose a path that seems almost deliberately designed for optimal planetary encounters. The precision of this trajectory has prompted some researchers to question whether we're witnessing natural celestial mechanics or something far more intentional. Such mathematical precision in cosmic trajectories typically requires either extraordinary coincidence or deliberate planning. Suspicious planetary encounters. The planetary encounter sequence of 3I Atlas reads like a carefully choreographed cosmic ballet that defies statistical probability. Robert Warwick from the University of Western Ontario, who previously discovered Oumuamua, has analyzed the object's path and found it passes unusually close to Venus, Mars, and Jupiter during its solar system transit. The probability of such close encounters occurring randomly has been calculated at an astounding 0.005%. Essentially impossible by chance alone. But the timing gets even more suspicious. Paul Chodas from NASA's Center for Near-Earth Object Studies has determined that 3I Atlas reaches its closest approach to the Sun precisely when Earth would be positioned on the opposite side, blocking direct observation during the most critical phase of its visit. The statistical probability of this alignment? A mere 7% chance. Karen Meach from the University of Hawaii has noted that rather than resembling the chaotic path of a randomly ejected comet, the trajectory appears optimized for studying the inner solar system planets while minimizing detection risks. This orbital choreography provides optimal vantage points for comprehensive planetary observations, exactly what you'd expect from a reconnaissance mission rather than a chance cosmic encounter. The mathematical precision required for such a trajectory suggests either unprecedented natural coincidence or deliberate design by an intelligence capable of interplanetary navigation. Physical properties and anomalies. The physical characteristics of 3I/Atlas are equally perplexing and honestly challenge our understanding of typical interstellar objects. Daryl Seligman from Michigan State University has determined that the object measures somewhere between 1 to 12 kilometers in diameter, making it significantly larger than both previous interstellar visitors and providing an unprecedented opportunity for detailed study. Spectroscopic analysis suggests this cosmic wanderer is extraordinarily ancient, potentially 7 billion years old, predating our entire solar system by billions of years. This makes it a genuine cosmic fossil, carrying secrets from the early epochs of our galaxy. Quanzi Ye from the University of Maryland has confirmed that 3I/Atlas is the brightest interstellar object ever observed, allowing for detailed spectroscopic analysis that just wasn't possible with previous visitors. Perhaps most intriguingly, the object exhibits a 29-hour rotation period with minimal brightness variation, suggesting either a spherical shape or a uniform surface composition, characteristics that are pretty unusual for natural comets. Matthew Knight from the Naval Research Laboratory has noted that high-resolution observations reveal a remarkably compact and dense appearance, lacking the typical fuzzy, diffuse structure expected from ancient comets. These physical properties suggest either an unusually well-preserved natural object or something with a fundamentally different composition and structure than anything we've previously encountered in our solar system. Comet-like features versus anomalous behavior. Here's where 3I/Atlas becomes truly enigmatic. It displays some comet-like characteristics while simultaneously exhibiting behavior that frankly just defies cometary physics. Alan Fitzsimmons from Queen's University Belfast has confirmed that the object shows a faint coma and a short tail measuring approximately 3 arc-seconds, indicating active outgassing as solar radiation heats its surface. Spectroscopic observations have detected the characteristic signature of sublimating water ice, producing the dust and gas envelope typical of approaching comets. However, Tony Farnham from the University of Maryland has noted several anomalies that challenge this interpretation. Despite its proximity to the Sun and evidence of outgassing, 3I/Atlas maintains a remarkably compact, dense appearance that differs dramatically from the fuzzy, diffuse structure of typical comets. Most puzzling is the absence of an expected extended tail, which really should be prominent given the object's size and solar distance. Bin Yang from the European Southern Observatory has observed that the outgassing patterns don't follow standard cometary models, with irregular brightness variations that suggest complex subsurface processes. The combination of active sublimation with maintained structural integrity presents a paradox. How can an object simultaneously behave like a comet while retaining characteristics more consistent with a solid engineered structure? This contradiction has sparked intense debate about whether we're observing natural cometary processes or something fundamentally different masquerading as a comet. Scientific debate: natural versus artificial. The scientific community has erupted into heated debate over the true nature of 3I/Atlas, with interpretations ranging from exotic natural phenomena to, well, potentially artificial origins. Avi Loeb, the Frank B. Baird Jr., professor of science at Harvard University, has emerged as the most vocal proponent of considering artificial origins, pointing to the statistically improbable trajectory and suspicious timing as evidence that, in his view, warrants serious investigation. Loeb argues that the mathematical precision of the object's path, combined with its optimal positioning for planetary reconnaissance, exceeds reasonable expectations for random cosmic events. His Galileo project at Harvard has been mobilized to conduct systematic observations using multiple telescopes worldwide. However, mainstream astronomers have pushed back strongly against these suggestions. Sarah Seeger from MIT acknowledges the unusual characteristics while emphasizing the importance of exhausting natural explanations before considering extraordinary possibilities. Robert Yedecke from the University of Hawaii has criticized speculation about artificial origins as premature and potentially damaging to scientific credibility. The debate highlights fundamental questions about how we interpret anomalous data and the threshold of evidence required for paradigm-shifting discoveries. Alan Stern, principal investigator of the New Horizons mission, has noted that while the characteristics are unusual, the universe is full of phenomena that initially appear impossible until we develop a better understanding of the underlying physics. Spectral analysis mysteries. The spectroscopic data from 3Y Atlas is revealing some puzzling inconsistencies that are, honestly, challenging our understanding of interstellar object composition. Stephanie Malam from NASA Goddard Space Flight Center has been coordinating observations using the James Webb Space Telescope to conduct detailed infrared spectroscopy of the object's composition. Initial results confirm the presence of water-ice spectrum, but the patterns just don't match our expected models. Jacqueline Keene from Boston University has identified these anomalous spectral signatures, where the observed signals actually increase in regions where water-ice models predict they should decrease. This contradiction suggests either unknown compositional elements or maybe structural properties that don't conform to standard cometary models. Now the object exhibits a distinctly reddish coloration, similar to objects in our outer asteroid belt, yet its interstellar origin kind of rules out formation in our solar system. Michelle Bannister from the University of Canterbury has noted that attempts to determine precise composition are complicated by the active coma surrounding the nucleus, which creates interference in spectral measurements. Julie Castillo-Roges from NASA's Jet Propulsion Laboratory has suggested that these unusual spectral characteristics might indicate exotic ice compositions or internal structures not found in solar system objects. So, these spectroscopic mysteries really add another layer of intrigue to an already enigmatic visitor, suggesting that 3I Atlas may be composed of materials or structured in ways we just don't yet understand. Dark forest hypothesis implications. The behavior patterns of 3I Atlas align remarkably well with theoretical models of how an advanced civilization might conduct reconnaissance while avoiding detection. The dark forest hypothesis, popularized by Chinese science fiction author Liu Cixin, suggests that intelligent civilizations remain hidden to avoid potential threats from other species. Seth Shostak from the SETI Institute has noted that 3Y Atlas exhibits what could be interpreted as stealth-like behavior, deliberately timing its closest solar approach when Earth would be positioned to block optimal observation. This timing ensures that the most detailed study phase occurs when our planet's scientific instruments have limited access to the visitor. Jill Tarter, former director of SETI research, has observed that the trajectory allows for comprehensive surveying of inner solar system planets, while minimizing exposure to potential detection by any resident intelligence. The orbital path provides optimal vantage points for studying Earth's atmosphere, Mars's surface conditions, and Venus's cloud dynamics, exactly the type of data an exploring civilization would prioritize. Frank Drake, creator of the famous Drake equation, noted before his passing that such reconnaissance patterns would represent logical exploration strategies for risk-averse civilizations. While most scientists remain skeptical of artificial explanations, the behavioral patterns of 3I Atlas do match theoretical models of how cautious interstellar explorers might operate when encountering potentially inhabited star systems. Historical context and lessons. The discovery of 3I Atlas comes with profound lessons learned from our missed opportunities with previous interstellar visitors. When 1I Oumuamua was discovered in 2017, the scientific community was caught completely unprepared for studying such a rare phenomenon. Robert Warwick, who discovered Oumuamua using the Pan-STARRS 1 telescope, has reflected on how the object's rapid departure left many critical questions unanswered. The mysterious acceleration exhibited by Oumuamua without visible outgassing remains unexplained to this day, highlighting the importance of comprehensive observation campaigns. Gennady Borisov, the amateur astronomer who discovered 2I Borisov in 2019 from his observatory in Crimea, provided the astronomical community with a second chance that was better utilized. However, even Borisov's study was limited by available technology and coordination protocols. Mark Norris, from the University of Central Lancashire, has emphasized that 3I Atlas represents our most comprehensive opportunity yet to properly study an interstellar visitor with advanced instruments and coordinated global observation campaigns. The improved detection capabilities of modern sky surveys, combined with rapid communication networks, have enabled real-time coordination among observatories worldwide. Michelle Bannister has noted that the lessons learned from previous interstellar encounters have fundamentally changed how the astronomical community approaches these rare events, ensuring that we're better prepared to unlock the secrets these cosmic messengers carry from distant star systems. Future observations and implications. The coming months represent a critical window for determining the true nature of 3I Atlas before it departs our solar system forever. Perihelion is scheduled for October 30, 2025, after which the object will begin its journey back toward interstellar space. Paul Chodas has calculated that 3I Atlas will re-emerge from behind the Sun in December 2025, providing a final opportunity for detailed observations before it becomes too distant for meaningful study. Karen Meach is coordinating an unprecedented international observation campaign involving over 50 professional observatories and numerous space-based instruments. The Hubble Space Telescope, James Webb Space Telescope, and ground-based facilities including the Very Large Telescope in Chile are all dedicating precious observation time to this cosmic visitor. Daryl Seligman has noted that the data collected during this campaign will either confirm 3I Atlas as an exotic but natural interstellar comet, or potentially revolutionize our understanding of what's possible in our cosmic neighborhood. The implications extend far beyond pure astronomy. If 3I Atlas proves to be artificial, it would fundamentally alter humanity's perspective on our place in the universe and our approaches to planetary defense and interstellar communication. Alan Fitzsimmons emphasizes that regardless of the final interpretation, 3I Atlas represents a pivotal moment in astronomy, where advanced technology meets unprecedented opportunity to study materials and possibly intelligence from beyond our solar system. As 3I Atlas continues its mysterious journey through our solar system, it challenges everything we thought we knew about interstellar visitors. Whether this ancient wanderer is an exotic natural phenomenon or something far more extraordinary, it's forcing us to expand our understanding of what's possible in the cosmos. The next few months will be crucial in determining the truth about this enigmatic visitor before it disappears back into the depths of space. Stay tuned to InnoVision Tech for the latest updates on this cosmic mystery. Like, share, and subscribe. Humanity's farthest messengers are about to fall silent, but a plan is already taking shape to send a successor. For nearly 50 years, the Voyager probes have been our eyes and ears in the void, but their 1970s technology is fading. Now scientists are designing a true interstellar explorer, a robotic probe built to fly faster, see clearer, and journey deeper into the cosmic ocean than ever before. This is the story of the mission to build Voyager's heir. Let's explore this together. The original Voyager achievement. Ever wonder how two probes from the 1970s became the greatest explorers in human history? The answer is a mix of brilliant engineering and perfect timing. Managed by the Jet Propulsion Laboratory, Voyager 1 and Voyager 2 launched in 1977, taking advantage of a rare planetary alignment that happens only once every 175 years. This Grand Tour alignment allowed them to use gravity assists, slingshotting from one giant planet to the next. Under the guidance of scientists like the legendary project scientist Ed Stone, who served for 50 years, the discoveries were staggering. We saw active volcanoes spewing sulfur on Jupiter's moon Io, confirming 9 active eruptions and making it the most geologically active object in the solar system. We discovered the icy geysers of Neptune's moon Triton, a world so cold it spews nitrogen frost. These missions completely rewrote planetary science textbooks, all accomplished with custom-built computers that had just 69.63 kilobytes of memory, less than 1/1,000,000th of a single photo taken by a modern smartphone. They transformed our view of the outer planets from fuzzy telescope images into a detailed family portrait, revealing worlds more dynamic and complex than anyone had ever imagined. It was a mission of firsts, providing the data that forms the foundation of modern planetary science. The journey into interstellar space. But their planetary tour was just the first act. Once their primary mission ended in 1989 after the Neptune flyby, the Voyagers just kept going, beginning the Voyager interstellar mission. Powered by their radioisotope thermoelectric generators, they traveled onward toward the boundary of our solar system. That boundary is the heliopause, the edge of the vast magnetic bubble our sun creates called the heliosphere. In August 2012, Voyager 1 finally crossed that boundary at a distance of 121 astronomical units, or 11 billion miles from the Sun. The moment was confirmed by Don Gurnett and his team at the University of Iowa when the Plasma Wave System instrument detected the vibration of dense interstellar plasma, a 40-fold increase in density that sounded like a sudden tone in the data. It was the sound of leaving home. Voyager 2, which took a different route past Uranus and Neptune, followed in November 2018, crossing at a different point in our solar bubble and giving us a second, crucial data point. Right now, Voyager 1 is over 15 billion miles away, hurtling along at 38,000 miles per hour. This was a monumental achievement, marking the first time a human-made object had physically entered the space between the stars, our first tangible step into the larger galaxy. Current limitations of the Voyagers. Here's the fundamental problem. The Voyagers are technological marvels, but they are also relics. They were designed for the powerful environments of planets, not the subtle nuances of interstellar space. Their magnetometers, for example, were built to measure the powerful magnetic fields of gas giants, not the faint, tenuous fields between the stars. Their cosmic ray subsystem can detect energetic particles, but it lacks the sophistication to distinguish between different heavy elements with the precision a modern instrument could, which is critical for understanding the origin of these rays. Furthermore, their power source, which uses heat from decaying plutonium-238, is fading. The initial 470 watts of power has dwindled, losing about 4 watts of electrical power each year. To conserve what little energy remains, engineers on the ground are in a constant race against time, making difficult choices about which instruments to sacrifice next. Their data trickles home to the Deep Space Network at a mere 160 bits per second, meaning it would take over a week to send a single low-resolution photo. The signal is now so faint, billions of times weaker than a watch battery, that it requires the world's most sensitive radio antennas just to hear it. The case for Voyager 3. This is where the idea for a successor, which many call Voyager 3, becomes more than just a dream. While Voyager 3 isn't an official NASA name, it perfectly captures the spirit of a next-generation mission. The actual, formal concept being studied at the Johns Hopkins Applied Physics Laboratory for NASA is called the Interstellar Probe. Led by scientists like Principal Investigator Dr. Elena Provornikova, this would be humanity's first spacecraft specifically designed to explore interstellar space. Its entire purpose would be to journey beyond the Sun's influence, born from the questions the Voyagers raised but could not answer. The goal is to build a probe that could operate for a minimum of 50 years and travel at a target speed of over 95,000 miles per hour. This incredible velocity would allow it to reach the heliopause in about 15 years, a journey that took Voyager 1 over 35 years. The mission's target isn't just the edge of the heliosphere, but a destination of 1,000 astronomical units into the truly undisturbed local interstellar medium. This distance is crucial because it's far enough away to be free from the Sun's lingering influence, allowing us to sample the pristine material of our galaxy for the first time. Advanced technology capabilities. So what kind of upgrade would a modern interstellar probe get? Let me explain. Compared to the Voyager's 1970s technology, a new probe would be a revolutionary leap. Instead of limited sensors, it would carry a suite of advanced instruments, a plasma spectrometer, energetic particle detectors, magnetometers, and a dust counter, all with at least 100 times the resolution of the Voyager's equipment. Power would come from a next-generation RTG, designed for longevity and providing enough power to run a full suite of instruments for a century. But the real game changer would be its brain AI-powered autonomous systems. This would allow it to make its own decisions, acting like a true robotic field scientist. It could prioritize data, compressing less important information to save bandwidth for groundbreaking discoveries, and even react to unforeseen events without waiting for the 3-day round-trip communication with Earth. To achieve its speed, the mission would launch on the most powerful rocket available, like NASA's SLS Block 2, and perform a powered Jupiter gravity assist, using both Jupiter's gravity and an onboard engine to achieve velocities previously thought impossible for a long-duration science mission. The interstellar medium mystery. Why is this so critical? Because our entire solar system is hurtling through a cosmic ocean, and we barely know anything about the water. This ocean is the interstellar medium. Our sun's solar wind carves out the heliosphere, which shields us from about 75% of the most energetic galactic cosmic rays. This shield works because the solar wind's outward pressure physically pushes away this deadly radiation. But what is its true shape? For years we thought it was a comet-shaped teardrop. However, models by scientists like Merav Ofer now suggest it might be a sphere or even a deflated croissant. A key unresolved question is how the interstellar magnetic field drapes around our heliosphere, which is crucial for its structure and how it protects us. Our solar system is currently passing through what's known as the local interstellar cloud, a slightly denser region of gas and dust. An interstellar probe could tell us how this local weather directly impacts the shape and strength of our protective bubble. Understanding this interaction is fundamental to understanding our own cosmic environment. Scientific objectives and research goals. Let's get specific. What questions would a mission like the interstellar probe finally answer? First, it would explore the unshocked interstellar medium, the pristine galactic material our sun is moving through. This means getting a baseline chemical inventory of our galactic neighborhood, the very stuff from which future stars and planets will form. Second, it would map the structure of our heliosphere in high definition, crossing key boundaries like the termination shock and heliosheath with far more advanced instruments. It would finally solve the mystery of its shape and reveal the physics of its interaction with the galaxy. Finally, the mission would journey to a target of 1,000 astronomical units from the Sun. As physicist Ralph McNutt from the APL team emphasizes, getting to this distance would allow us to look back and view our solar system as a complete astrosphere for the first time. From this vantage point, it could even detect the faint extragalactic background light without interference from dust in our solar system, opening a new window for cosmology and studying the universe's first light. It would be a multi-purpose observatory unlike any other. Practical applications for future missions. This isn't just about abstract science, it's about laying the groundwork for humanity's future in space. Let me explain. Any future attempts at sending probes to other star systems will require navigating the interstellar medium. An interstellar probe would act as a pathfinder, creating the first detailed atlas of the space just outside our solar system. It would quantify the radiation risks for future robotic or human missions, which would be impossible without the precise data this probe would gather. At speeds over 90,000 miles per hour, even a tiny grain of interstellar dust can strike with the kinetic energy of a rifle bullet. So the probe would map dust density to inform shielding design for future, even faster craft. Developing the technology to reliably communicate with a probe hundreds of AU away would push our deep space communication capabilities, benefiting all future missions. Furthermore, it would pioneer techniques for autonomous interstellar navigation, a requirement for any craft that travels so far from home that the sun becomes just another bright star. This is essential for concepts like breakthrough starshot, which would need this data to even begin planning. Cultural significance and golden record 2.0. What message would you send to represent all of humanity on a journey that will outlast everyone alive today? In 1977, Carl Sagan's committee assembled the Golden Records. An interstellar probe would carry on this legacy, but a Golden Record 2.0 wouldn't be a physical disc. John Lomberg, the artist who designed the original record's cover, has proposed a digital successor. This new archive could hold petabytes of data, the entire human genome, vast libraries of art and science, and perhaps even messages from the public. The new message would have to reflect our more globalized, digitally connected, and perhaps more self-aware civilization. The very act of creating it forces us to reflect on our collective identity and what we would want to say about ourselves to the cosmos. How do you represent humanity's flaws alongside its triumphs? Who gets to decide? This probe and its message will travel through the galaxy for millions of years, long after Earth has changed beyond recognition. It serves a dual purpose, a scientific instrument pushing the frontier of knowledge, and a cultural artifact carrying the story of humanity to the stars, a true monument to our civilization. Timing and opportunity. Here's the bottom line: if we want to do this, the clock is ticking. The Voyagers completed their grand tour because of a rare planetary alignment. To achieve the incredible speeds needed for this new mission, the interstellar probe would also rely on a gravity assist from Jupiter. The APL study pinpoints an optimal launch window in the early 2030s. The plan is to launch on a powerful rocket like NASA's Space Launch System and then perform an O-berth maneuver, firing its own engine at its closest approach to Jupiter to get the maximum possible boost. Missing this window could mean delaying the mission for another decade or more, waiting for the planets to once again align for such an efficient trajectory. A mission launching in the 2030s needs to be approved and funded years in advance, meaning crucial decisions must be made in the coming years. This is a generational opportunity, a symbolic passing of the torch to ensure humanity's boldest journey of exploration continues. It requires foresight and a commitment to science that looks beyond immediate returns, a gift to the future. An interstellar probe wouldn't just be repeating the past, it would be a quantum leap forward. It would push deeper, answer fundamental questions about our place in the cosmos, and test the technologies needed for future missions to the stars. The first Voyagers were our first messengers to the galaxy, carrying a hopeful greeting from a small distant world. This new probe could be our new voice, our new eyes, and our first true step beyond the sun's embrace. Are we ready to take that step? Don't forget to like, subscribe, and hit the bell icon. Thank you for watching InnoVision Tech. What happens when our most advanced space monitoring technology captures an image that, just totally defies explanation, only for the data feed to be severed at that precise moment? On June 18th, NASA's live stream tracking 3I Atlas, our solar system's third interstellar guest, transmitted a single, baffling frame. It showed an object with characteristics that appeared honestly, unnervingly artificial, then nothing but static. The official report cited network failure, but cryptographically verified data from independent archivists confirms the image is real. So what was that razor-sharp glint in the void? Let's analyze the data together. The initial discovery. The story begins with a technological marvel of planetary defense. On July 1, 2025, the Asteroid Terrestrial Impact Last Alert System, a network of robotic telescopes better known as ATLAS, triggered an alert. This NASA-funded system, with University of Hawaii's Larry Deno as its principal investigator, scans the entire night sky every 24 hours. Its primary mission is to find near-Earth objects, but on this day, its algorithms flagged something extraordinary. The object's trajectory was hyperbolic, a clear mathematical signature indicating its velocity was far too great for it to be a member of our solar system. It was on a one-way ticket just passing through. The global astronomical community immediately mobilized, and within a day, the Minor Planet Center officially designated it 3Y Atlas, confirming it as just the third interstellar object ever detected. While early images showed the familiar coma and tail of a comet, its origin story was anything but familiar. This was an artifact from another star system, a rare opportunity that our technology, far more advanced than during the 2017 flyby of Oumuamua, was finally ready to seize. The anomalous frame. This is the moment a routine observation devolved into a profound enigma. The final frame broadcast from NASA's feed, captured at precisely 03:1712 UTC, initially seems unremarkable. The faint glow of the comet's nucleus, enveloped by its gaseous coma, is set against the cold vacuum of space. But in the lower left quadrant, a detail emerges that just violates the natural aesthetics of a comet. It's a glint of light, but it's not diffuse or scattered. It's a perfectly straight edge, a sharp, geometric line. Physicists identify this as specular reflection, the kind of clean bounce of light you get from a polished surface, not the chaotic scattering produced by a chunk of fractured ice and rock. This observation immediately brought to mind the work of researchers like Harvard's Avi Loeb and his Galileo project, which actively searches for extraterrestrial technosignatures. Independent analysts quickly ran the image through edge detection algorithms, which confirmed the anomaly, a line segment about 37 pixels long, presenting an angle and sharpness inconsistent with any known natural cometary phenomenon. The data pointed to a chilling possibility, that the light was reflecting off something manufactured. Data verification. In an age of digital manipulation, the first question is always, is the evidence authentic? This is where the power of modern data integrity and citizen science comes into play. Before any official statements were made, a global network of independent archivists had already secured the data. These individuals run automated scripts that continuously download and mirror raw data feeds from space agencies. Within minutes of the blackout, copies of the feed from Australia, Germany, and the United States were uploaded to public servers. Each file, carrying the identical 03/1712 UTC timestamp, was validated with a unique SHA-256 checksum. This cryptographic hash functions as an incorruptible digital fingerprint. Altering even a single pixel would result in a completely different hash. When every copy was compared, they were all identical. The chain of custody was flawless, from NASA's original relay to the decentralized archives. This rigorous process proved the anomalous frame was not a hoax or a transmission error. The data is immutable, the archives are clean, and the mystery, as the celebrated astronomer Carl Sagan often emphasized, is therefore deserving of serious scientific inquiry because the foundational evidence is verifiable by anyone. Technical explanations. If the data is real, could the blackout be a staggering coincidence? To answer that, we have to look at the technology involved. NASA's communications architecture is, a global machine. It relies on the Deep Space Network, or DSN, with its massive radio antennas in Goldstone, California, Madrid, Spain, and Canberra, Australia. This system works in concert with the Tracking and Data Relay Satellite System, a constellation first launched in 1983, to provide continuous contact with probes and telescopes. Signal dropouts are a normal part of operations. As the Earth turns, a spacecraft will dip below the horizon of one DSN station, requiring a signal handover to the next. Sometimes this process, managed by engineers like JPL's Bradford Arnold, isn't perfectly seamless, causing a brief interruption known as a handover blank. These routine events are meticulously logged with specific reason codes. However, the outage at 0317 UTC, occurring at the exact second the anomaly was visible, did not have a standard handover code in the public logs. The official explanation cited general network instability, but the uncanny timing and lack of a specific technical fault code has left many experts and observers deeply unsatisfied. Digital forensics. Now let's zoom in to the pixel level, where the digital reality of the image is forged. Forensic analysis of the final frame revealed two critical clues that could point to a non-exotic explanation. First, the glint's straight edge aligns perfectly with the boundaries of several 8x8 pixel blocks. This is a telltale sign of how video compression algorithms like MPEG function. To reduce file size for transmission over vast distances, these codecs divide the image into a grid and can sometimes amplify or quantize a faint, noisy line into an unnaturally sharp, blocky one. The second clue involves cosmic rays. Deep space is saturated with high-energy particles that can strike a camera's sensor and overload a few pixels, creating a bright, transient streak that lasts for only a single frame. Digital forensics experts like Professor Hani Farid have documented how common these sensor-level events are in space imaging. Therefore, a leading theory proposes a double-hit scenario. A cosmic ray created a faint, linear artifact on the sensor, which was then exaggerated by the compression codec into the illusion of a perfect solid edge. It's a plausible, purely technical explanation, though the brightness and consistency of the glint still push the boundaries of a typical artifact. 3-eye atlas background. To truly grasp the significance of the anomaly, we must understand the object itself. Even before the controversial frame, 3-eye atlas was a scientific puzzle. Detailed spectroscopic data from the James Webb Space Telescope, analyzed by teams including researchers like Martin Cordner at NASA's Goddard Space Flight Center, revealed a startling chemical composition. Unlike most comets from our own solar system's Oort cloud, such as the famous comet Hale-Bopp from 1997, which was rich in water ice, 3-eye atlas was overwhelmingly dominated by carbon dioxide. It had a CO2 to water ratio of nearly 8:1. This means carbon dioxide ice, not water ice, was the primary fuel for its spectacular outgassing, creating a massive coma that stretched for hundreds of thousands of kilometers. This dense gaseous shroud completely hid the nucleus from direct view, with estimates placing its diameter at under a kilometer, comparable to the second interstellar visitor, 2I Borisov, which passed through in 2019. The Atlas survey's rapid scanning capability allowed for its early detection, giving us a precious opportunity to study it. This unique chemistry already confirmed it was an alien object, formed in a star system profoundly different from our own. Scientific scrutiny. In science, and especially in the search for extraterrestrial intelligence, skepticism is, well, the default position. Any extraordinary claim must survive a trial by fire. An anomalous signal in a single frame from one instrument is merely the starting point, not the conclusion. You see, the guiding principle is that extraordinary claims require extraordinary evidence. For the glint on 3I Atlas to be considered a credible techno-signature, it must be independently confirmed by other observatories using different instruments, preferably across multiple wavelengths of light. This is how science separates a true signal from instrumental noise or an artifact. As of now, the evidence remains on the lowest rung of this ladder of proof. We have a single, tantalizing data point, but no corroborating observations. Until the Hubble Space Telescope, the JWST, or major ground-based observatories can produce matching data, the majority of the scientific community, including veteran SETI astronomers like Jill Tarter, will urge caution. It's a slow, rigorous process designed to ensure that when a discovery is announced, it is built on a foundation of undeniable, repeatable evidence, preventing the kind of historical misinterpretations like Percival Lowell's belief in Martian canals. 3 theories. The debate over the anomaly has coalesced into 3 competing hypotheses. The first is grounded in conventional cometary physics. Comets are chaotic bodies. The intense solar heating experienced by 3I Atlas could have caused thermal stress, fracturing the nucleus and cleaving off a large, flat shard of ice or rock. The unusual glint could be nothing more than a brief reflection of sunlight off this newly exposed, highly reflective surface. The second theory points to a technological illusion. This is the Occam's razor explanation, suggesting the edge is simply a convergence of unrelated phenomena. A cosmic ray striking the sensor at a shallow angle, its effect amplified and distorted by the video codec's blocky math. It's a ghost in the machine. But the third idea, the one that challenges our assumptions about the universe, refuses to be dismissed. This hypothesis, echoing the speculative work of physicists like the late Freeman Dyson, posits that the object is exactly what it appears to be, manufactured. Perhaps it's a component of a self-replicating von Neumann probe, a fragment of a light sail, or a piece of a protective shell. The odds are admittedly long, but the data is just ambiguous enough to keep the possibility on the table. Broader implications. An event like this, a mysterious signal followed by an unexplained data blackout, has consequences that extend far beyond the astronomical community. It becomes a catalyst for public debate and a driver of scientific policy. The conversation shifts from what is that object to who controls the data and the narrative of discovery. It amplifies calls for greater transparency and the development of open-source data platforms, a principle that is driving next-generation projects like Chile's Vera C. Rubin Observatory. For the public, it's a powerful lesson in critical thinking, reminiscent of the global reaction to the famous 1977 WOW signal. That powerful, unexplained radio burst detected by astronomer Jerry Amon remains a cornerstone of SETI lore. This incident with 3I Atlas forces a conversation about our technological and psychological readiness for a potential first contact scenario. It challenges international bodies like the UN's Committee on the Peaceful Uses of Outer Space to consider protocols for such an event. It perfectly illustrates the tension between rigorous skepticism and the profound sense of wonder that fuels our exploration of the cosmos. The search continues. So, where does this leave the investigation? The official record is clear on a few facts. At 0317 UTC, the NASA feed was cut. The final frame contains a cryptographically verified geometric anomaly. The blackout's timing, while officially attributed to network issues, is highly suspect. As of today, no conclusive, peer-reviewed evidence exists to support an artificial origin for the glint on 3I Atlas. However, the search for answers is accelerating. Ambitious new missions are already in development, most notably the European Space Agency's Comet Interceptor. Scheduled for launch around 2029, this innovative spacecraft will park itself at a stable Lagrange point in space, essentially lying in wait for the next long-period comet or interstellar visitor to arrive. It will then be deployed for a close-range flyby, giving us our first high-resolution look at one of these pristine objects. This proactive strategy, championed by scientists like the mission's lead, Geraint Jones, demonstrates a paradigm shift in how we study these cosmic messengers. Every interstellar visitor is a gift, pushing our technology and our theories to their limits. The strange case of 3I Atlas remains one of the most compelling technological mysteries of our time, caught between a plausible digital artifact and a discovery that could reshape the future of humanity. The verified data presents an anomaly, but the ultimate explanation is still out there, traveling through the darkness of our solar system. What is your analysis? Was this a ghost in the machine, a 1 in a billion natural coincidence, or our first fleeting data point from a technology beyond our own? Share your hypothesis in the comments below. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the technology that is shaping our future. Thanks for watching InnoVision Tech. A mysterious object is racing toward our solar system at incredible speed, and scientists are scrambling to understand what it really is. In the summer of 2025, astronomers made a discovery that has sent shockwaves through the scientific community. A massive visitor from interstellar space that's unlike anything we've ever encountered. Some researchers are asking the unthinkable question, could this be something artificial? Today we'll explore the mind-bending discovery of 3I Atlas, and investigate whether we might be witnessing our first contact with alien technology. A rare visitor from deep space. Picture this. You're looking up at the night sky, completely unaware that something extraordinary is racing toward us from the depths of interstellar space at unimaginable speed. In the summer of 2025, astronomers detected exactly that, a massive cosmic wanderer that has been traveling through the galaxy for potentially billions of years before finally entering our solar system. This isn't just any ordinary asteroid or comet from our familiar cosmic neighborhood. This is 3I Atlas, a visitor from another star system entirely, carrying with it secrets from the far reaches of our galaxy that could revolutionize our understanding of how planetary systems form and evolve. What makes this discovery absolutely mind-blowing is that we're witnessing only the third confirmed interstellar object ever detected in human history. The rarity of such encounters means that most of us will never see another visitor like this in our lifetimes. As 3I Atlas races through our solar system at 61 kilometers per second, it's providing scientists with an unprecedented opportunity to study materials that originated around a completely different star, potentially offering our first glimpse into the composition and characteristics of distant worlds we may never be able to visit directly. The breaking discovery. Here's the moment that changed everything we thought we knew about our cosmic neighborhood. The discovery of 3I Atlas represents only the third confirmed interstellar object ever detected passing through our solar system, placing it in an extraordinarily rare category of cosmic visitors. To put this rarity in perspective, astronomers estimate that only one interstellar object larger than 100 meters crosses our solar system annually. Yet most remain completely undetected due to their incredible speed and darkness. Robert Jedicka from the University of Hawaii has calculated that detecting these objects requires perfect timing and cutting-edge technology working in harmony. The significance of 3I Atlas cannot be overstated. It joins the legendary 1I Oumuamua discovered in 2017 and 2I Borisov found in 2019 as the only confirmed messengers from other star systems. What makes this discovery particularly groundbreaking is its massive size and unusual characteristics that are forcing scientists to reconsider their understanding of interstellar objects. Unlike typical asteroids or comets from our solar system, these visitors carry secrets from distant star systems, potentially harboring materials and information that could revolutionize our understanding of planetary formation, galactic evolution, and perhaps even the possibility of life beyond Earth. Each new interstellar detection brings us closer to understanding the true nature of our galaxy's wandering population. The discovery story. The incredible story of how we discovered this cosmic wanderer began in the final days of June 2025, when the Atlas telescope system at Rio Hurtado Observatory in Chile captured something extraordinary moving against the starfield. Larry Deneau, a key member of the Atlas survey team at the University of Hawaii, was conducting routine observations when the automated detection software flagged an unusual fast-moving object. The initial designation A11PL3Z was assigned to this mysterious visitor as astronomers worldwide scrambled to confirm its interstellar origin. John Tonry, the principal investigator of the Atlas project, immediately coordinated with observatories across the globe to track the object's trajectory and confirm its hyperbolic orbit. Within 48 hours of detection, follow-up observations revealed pre-discovery images dating back to June 14, 2025, indicating the object had been silently approaching our solar system for weeks. The challenge of detecting 3I Atlas stemmed from its path through the dense star fields near Sagittarius, where countless background stars made it nearly invisible against the crowded stellar backdrop. Once confirmed as an interstellar visitor, the Minor Planet Center officially designated it as 3Y Atlas, marking a historic moment in astronomy. This rapid confirmation process demonstrated the remarkable advancement in our ability to detect and track these rare cosmic messengers. A stranger in our midst. Alright, get ready to be amazed by the extraordinary characteristics that make 3I Atlas unlike any object we've ever studied in our solar system. This interstellar giant is racing through space at a mind-boggling 61 kilometers per second relative to our Sun. A velocity so extreme it actually proves the object originated from beyond our solar system's gravitational influence. Marco Michelli from the European Space Agency has determined that 3Y Atlas measures approximately 11.2 kilometers in diameter, making it significantly larger than both previous interstellar visitors combined. To put this massive scale in perspective, this cosmic wanderer is roughly the size of a small city, totally dwarfing the mysterious Oumuamua, which measured only about 400 meters in length. Daryl Seligman from Michigan State University pointed out that the object's brightness and size make it an unprecedented target for detailed scientific study. Unlike typical solar system objects that follow predictable elliptical orbits around the Sun, 3I Atlas follows a hyperbolic trajectory that will carry it back into the depths of interstellar space. The comet has developed a spectacular 25,000-kilometer-long tail as solar radiation heats its ancient ices, creating a magnificent display visible through powerful telescopes. This combination of extreme size, speed, and activity makes 3I Atlas a once-in-a-lifetime opportunity for astronomical research. The predecessors. To understand the true significance of 3I Atlas, we really need to look back at the groundbreaking discoveries that paved the way for this moment. The very first interstellar visitor, 1I Oumuamua, was discovered on October 19, 2017 by Robert Warwick using the Pan-STARRS 1 telescope in Hawaii. This cigar-shaped object, measuring roughly 400 meters long, totally baffled scientists with its unusual tumbling motion and mysterious acceleration that couldn't be explained by gravitational forces alone. Avi Loeb from Harvard University famously proposed that Oumuamua might be artificial in origin, sparking some pretty intense debate in the scientific community. 2 years later, amateur astronomer Gennady Borisov discovered 2Y Borisov on August 30, 2019 from his observatory in Crimea. Unlike the enigmatic Oumuamua, Borisov behaved like a typical comet, developing a coma and tail as it approached the Sun. Alan Fitzsimmons from Queen's University Belfast led extensive spectroscopic studies that revealed Borisov's composition was remarkably similar to comets in our own solar system. These discoveries established that interstellar objects come in different varieties, some mysterious and unusual like Oumuamua, others more familiar like Borisov. The cosmic journey. So let's follow the incredible path this ancient wanderer will take as it sweeps through our solar system over the coming months. Davide Farnochia from NASA's Jet Propulsion Laboratory has precisely calculated that 3Y Atlas will reach its closest approach to the Sun, called perihelion, on October 29, 2025 at exactly 11:41 Universal Time. At this critical moment, the comet will be positioned 1.36 astronomical units from the Sun, about 203 million kilometers away, perfectly situated between the orbits of Earth and Mars for optimal observation conditions. This cosmic dance includes several remarkable planetary encounters that provide unique scientific opportunities. On October 3, 2025, the comet will pass just 0.19 astronomical units from Mars, only 28 million kilometers away, potentially allowing Mars-based instruments to conduct unprecedented close-range observations. Following its solar encounter, 3Y Atlas will swing past Venus on November 3, 2025 at a distance of 0.65 astronomical units before beginning its journey back to interstellar space. Earth remains completely safe throughout this celestial ballet, with the closest approach occurring on December 19, 2025 at a comfortable distance of 1.8 astronomical units, or about 270 million kilometers. This trajectory provides astronomers with multiple observation windows and vantage points throughout the solar system, maximizing scientific opportunities. A scientific gold mine. The arrival of 3I/Atlas represents, honestly, an unprecedented scientific opportunity that has mobilized the global astronomical community like never before. Karen Meach from the University of Hawaii is leading an international consortium of researchers conducting comprehensive studies of the comet's composition, structure, and behavior. The James Webb Space Telescope, under observations coordinated by Stephanie Milam from NASA Goddard Space Flight Center, has been scheduled to conduct detailed infrared spectroscopy to identify complex organic molecules within the comet's nucleus. Alan Fitzsimmons from Queen's University Belfast has already detected unusual isotopic ratios in the comet's gas emissions using the Gemini Observatory, suggesting formation conditions vastly different from our local environment. Ground-based facilities including the Very Large Telescope in Chile and the Keck Observatory in Hawaii are providing continuous monitoring of brightness changes and spectral evolution. Bin Yang from the European Southern Observatory has identified traces of exotic water vapor with unusual deuterium concentrations, indicating the comet formed in an extremely cold environment around a different type of star. This coordinated global campaign represents the most comprehensive study of an interstellar object ever conducted, with data collection providing insights into star formation processes, planetary system evolution, and the distribution of life-building molecules throughout our galaxy for decades to come. Unanswered questions. Despite intensive observations, 3I/Atlas continues to harbor profound mysteries that challenge our understanding of interstellar objects and their origins. Quanji Ye from the University of Maryland has been tracking unexpected brightness variations that just don't match typical cometary behavior, suggesting the object may have an unusual internal structure or composition. The comet's reddish coloration, observed by multiple telescopes worldwide, indicates the presence of organic compounds, but the exact nature of these materials, well, it remains unknown. Matthew Knight from the Naval Research Laboratory has noted that high-resolution Hubble Space Telescope images reveal intricate details in the coma structure that don't conform to standard comet models. One of the most perplexing aspects is the object's estimated age of 7 billion years, older than our entire solar system, which really raises questions about how such ancient materials have remained preserved during eons of cosmic radiation exposure. Tony Farnham from the University of Maryland has documented irregular outgassing patterns that suggest complex subsurface processes we honestly don't fully understand. The Discovery team, led by Daryl Seligman, acknowledges that many fundamental questions remain unanswered. What star system did it originate from? What caused its ejection into interstellar space? And perhaps most intriguingly, could there be more to this object than meets the eye? These mysteries ensure that 3I/Atlas will remain a subject of intense scientific scrutiny. The alien question. Here's where the discussion takes a fascinating and honestly controversial turn that has divided the scientific community. Avi Loeb, the Frank B. Baird Jr. Professor of Science at Harvard University and former chair of the Astronomy Department, has gained international attention for suggesting that some interstellar objects might be artificial in origin. Following his controversial proposals about Oumuamua, Loeb has expressed interest in 3I/Atlas, noting that its unusual characteristics warrant careful investigation of all possibilities, including artificial origins. Sarah Seeger from MIT has emphasized the importance of maintaining scientific rigor while remaining open to extraordinary possibilities, stating that we must examine every aspect of these rare visitors. The Galileo project, led by Loeb at Harvard, represents a systematic scientific approach to searching for evidence of extraterrestrial technology in our solar system. However, most mainstream astronomers, including Paul Chodas from NASA's Center for Near-Earth Object Studies, maintain that natural explanations can account for the observed properties of interstellar objects. Robert Warwick, discoverer of Oumuamua, has consistently argued that these objects, while unusual, fall within the expected range of natural cosmic phenomena. The debate really highlights the importance of maintaining scientific skepticism while remaining open to paradigm-shifting discoveries. Dawn of a new era. The discovery of 3I Atlas signals the beginning of a revolutionary era in astronomy, where interstellar objects will become regular subjects of scientific study, rather than once-in-a-lifetime discoveries. Mark Norris from the University of Central Lancashire predicts that advancing technology will soon make these detections routine, fundamentally changing how we study galactic dynamics and planetary system formation. The Vera Rubin Observatory, which began full operations in 2025, is expected to revolutionize interstellar object discovery with its ability to scan the entire visible sky every few nights using advanced LSST camera technology. Michelle Bannister from the University of Canterbury estimates that within the next decade, we'll have discovered dozens of these cosmic wanderers, providing statistical samples large enough to understand their origins and distribution throughout the galaxy. Robert Yadika from the University of Hawaii calculates that the improved Atlas survey system, now operating telescopes in Hawaii, Chile, and South Africa, will detect several interstellar objects annually. This technological revolution means that each new discovery will add pieces to the cosmic puzzle of how materials, and potentially life itself, are distributed throughout our galaxy. The age of interstellar archaeology has officially begun, promising to unlock secrets about distant worlds and the formation of our cosmic neighborhood that have remained hidden for billions of years. From its mysterious origins billions of years ago to its spectacular journey through our solar system, 3I Atlas has challenged everything we thought we knew about interstellar visitors. Whether it's a natural cosmic wanderer or something more extraordinary remains to be discovered. As this ancient traveler continues its path back to the stars, it leaves behind more questions than answers, and opens our minds to possibilities we're only beginning to imagine. Like, share and subscribe to InnoVision Tech for more incredible discoveries from the cosmos.